A couple of weekends ago, the weather guy reported that we were supposed to get like 6 inches of snow, and people started going crazy. Quick, buy all the bread and milk! But sooner or later, the weekend rolled around and there was hardly any snow, if any, and nobody made any Texas toast with all that bread and milk. So, should we fire the weather guy? Well, here's the thing. Weather is a complicated subject. It's based on a lot of data from history. It's also based on a lot of weather patterns and this thing called probability. Probability is defined as the likelihood of a given event happening. For instance, when I flip a coin, there's a probability that I could get a heads, or there's a chance I could get tails. When we talk about probability, we use a very intentional set of vocabulary to talk about the events. So let's look at an example. So let's say that we are testing a brass dog bone. We place the dog bone into the SSA machine, and our goal is to see how much force the dog bone can experience before breaking. This is our experiment. During the experiment, the dog bone could break anywhere from 0 pounds up to 1,000 pounds, or it could just not break at all. This is called our sample space, or the list of the possible outcomes. Let's say that one of the possibilities is that the dog bone could break under a load of 200 pounds. This would be a possible event. If the dog bone were to break at 200 pounds, this would be our outcome. So throughout this video, we'll use the example of flipping a coin, because it's pretty easy to think about. If I flip a coin, I either get heads or tails. There's a 50% chance of either outcome. When we think about probabilities, it helps us to think about it if we use this thing called a probability tree. A probability tree shows us all of the possible outcomes of a given experiment. So for flipping a coin, our two possible outcomes are heads or tails. After we've calculated a probability, we have two ways of expressing it. We can express it as a ratio of a number less than 1, like 0.45, or we could represent it as a percent, like 45%. When we talk about simple probabilities like flipping a coin once, we have an equation called the relative frequency equation. The relative frequency equation is f sub x is equal to n sub x over n. That's a lot of subscripts, so let's break this down. F sub x is the frequency of our desired outcome. The n sub x is the number of times that our success or our desired outcome happens. And the n on the bottom is the total number of possible events. So if we were to flip a coin once, our possible outcome would be 1 if it lands on heads. And the total number of outcomes possible would be 2. It either lands on heads or tails. So the probability, or the relative frequency, of getting a heads or a tails is 0.5, or 50%. But this equation allows us to look at some things that are a little bit more complicated. So what would be the probability of flipping a coin twice and getting heads both times? To think about this, we draw a probability chart. And if we look at it, there are a set of outcomes. In the first flip, we have two possible outcomes, heads or tails. When we flip the coin again, there are also two outcomes. So we have 4 possible outcomes, flipping heads then heads, flipping heads then tails, flipping tails then heads, or flipping tails then tails. But we only want one of those. We only want heads then heads. So we only have one desired outcome, but there are 4 total events. So our probability of flipping heads twice is 0.25, or a 25% probability. Let's look at an example problem. What is the probability of flipping 3 coins and getting heads exactly twice? To see this, we should draw a probability tree. When we do this, we can see each of the outcomes of our 3 flips, heads or tails. After 3 flips, we see that we have 8 total events. It's important when we use a probability tree to note that heads, heads, tails is not the same event as tails, heads, heads. Even though we have the same amount of heads and tails in each of these events, they are separate events. Looking at our probability tree, we see that we have 3 success events where we have exactly 2 heads. So that would be 3 out of 8 total. So f sub x would be 3 over 8, which is 0.375, or there's a 37.5% probability. So when we flip a coin, the outcome of that experiment has no impact on the second flip of the coin. But this isn't true for all events that we look at probability for. This type of event is called the binomial process, where the first possible experiment type doesn't affect the other one. But we may find that we need to deal with something that needs to have something more complicated, and we call this a Bernoulli process. The Bernoulli probability equation allows us to analyze complex sequences of events and only do the math once. It still helps us to do a probability tree sometimes, but it may not be possible for us to draw a probability tree depending on how many possible outcomes there are. Okay, math time, right? So in the Bernoulli equation, there's this thing called the factorial, and it looks like there's a number that's just really excited. What you'll see in a factorial is a number with an exclamation mark next to it. It doesn't mean that it's excited. It means that it's a function. So the factorial tells the number that it needs to be multiplied by all of the numbers in between it and 1. So for instance, 5 factorial is actually 5 times 4 times 3 times 2 times 1. The nice thing about this is that our scientific calculators actually have a factorial function, so we don't have to type in all of the integers between our number and 1. Fair warning, this equation's pretty crazy, but we can do this because our scientific calculator is pretty beefy and it can handle this math. Capital P sub x is equal to n factorial times little p to the x power times q to the n minus x power, all divided by x factorial times the quantity n minus x factorial. That's just totally disgusting, right? But we can do this if we break it down. So capital P stands for the probability of the event that we're looking at. The x stands for the number of times that our desired outcome occurs in a total of n trials. Little p is the probability of that event happening in a single trial, and little q is the probability of failure for that single event. So here's the nice thing about the Bernoulli equation. If we were to plug in the numbers for our coin flip example problem earlier, the math still works out. We would still get the probability of 37.5%. Let's look at another example problem.
You are taking a 10-question multiple choice test. If each question has 4 choices and you guess on each question, what is the probability of getting exactly 7 questions correct? Let's start by defining our information. We are looking for probability, which is capital P. There are 10 questions, so there are 10 total events, so that's our n. We want 7 successful questions, so that's our x. There are 4 choices in each question, so our chance of success for a single question is 25%, or 0.25, so that's our little p, which makes 0.75 our q. There's a 75% chance of failure. Now we plug in everything and solve for capital P. Using the factorial function on our calculator makes things a lot easier here. Our answer is 0.31% probability.
In our next video, we will be looking at statistics. A lot of people confuse probability and statistics, so just remember this. Probability deals with the chances or the odds of something happening in the future. Statistics is based on historical data, or things that have already happened. So statistics are based on the past, and probability is based on a potential future. But we'll talk more about that in our next video.